On the list is Thomas Pfeil. He will be presenting on site, right?
Yes.
Okay. Don't know if you pre-recorded the video or something.
You're running out of oxygen.
Yeah, I know it's getting
a bit tight, so to say. Okay, anyway.
Okay, so let me introduce you to Thomas Pfeil, who is currently working with Recogni, or Recogni, I don't know how to pronounce it correctly. He did his PhD at University of Heidelberg between 2011 and 2016. Then he worked at the IBM Research Lab in Almaden, San Jose, for a year. And after that, he joined Bosch, where he worked as a research engineer till 2022. And then he joined Recogni as a senior AI engineer. And he's going to talk about hardware-aware network compression from data to silicon today. So we're very excited to hear your talk. And thank you very much, Thomas.
All right, so thanks for introducing and having me today. So let me check. So how can I go to the next slide? Just using the computer? Right now it's working. Now it's working, perfect. Okay. So today I will talk about hardware-aware network compression. And I would like to start with my interpretation of what hardware algorithm co-design is. I think we heard a lot of it during the last days, but everyone I talked to has a different definition. Afterwards, I would like to talk about the difference between quantization-aware training and post-training quantization. And last but not least, I would like to jump into the details about a very specific, sophisticated pruning technique. Okay, so usually you have a task to solve. You have data with labels, you have some metrics, sometimes it's accuracy, and you have an associated loss to this matrix. Actually, is this the right set of slides from the Google Drive?
This is the link.
Okay, it's kind of outdated, but okay, I'll fill in the missing parts verbally. Because there's something missing here. What you also have in embedded devices is the constraints in terms of hardware. And this is usually something like runtime or memory. So if you would like to train a network, what do you need? You need to select the neural architecture. You need to parameterize the neural architecture. You have to select all the training parameters. So this means you look at literature, maybe you decide for a ResNet, then you decide for ResNet 50, and then you decide for the learning rate and batch size and so on. Then you train the network, and what do you get out of it? The task accuracy. Then, because you're resource constrained, you would like to compress the network. And for the compression, first you have to select the compression method, you have to configure that compression method, and you potentially want to fine-tune. And after fine-tuning, you get the accuracy of the compressed network. Then you have to compile your network graph. So there again, you have to configure the compiler, what trade-off to choose between computation and memory, and so on. And what you get out of it, for example, are the memory requirements. And last but not least, you would like to profile your compiled network on hardware. And there again, you have to specify what hardware to use and how to choose the dimensions. For example, take an array for matrix multiplication. You have to define the size of the array. You have to define the bandwidth. You have to define the precision and so on. And then if you run your network on hardware, you can record the runtime and the power. And what is usually done after each of these steps, usually you optimize the configuration to get the best task accuracy or to get the lowest runtime or power. And you do this individually for each of these steps. And you may have already noticed that this is actually the deployment process, like It's usually done in industry. And if you look at the upper part, these are all configurations for this deployment process. And if you look at the lower part, these are the evaluation of the final result and the intermediate steps. And usually, the compressed accuracy, runtime, and power are of highest interest. So instead of optimizing each of these blocks vertically, of course, we can do better. So we can actually close the loop across this whole deployment process. So this means all these configurations, all these blocks could be seen as a search space, and the evaluation could be seen as the cost function of this optimization. And this is how I understand hardware algorithm co-design. And by doing that, usually you get the best solution. But of course, this is not easy. There's a lot involved. And I remember 10 years ago, people called it hardware software co-design. And there's a lot of software included in that. Now let me give you a short overview of compression methods before I give you an example why this hardware algorithm co-design is very beneficial. All right. So one method, we already heard about it today, is knowledge distillation. You have an uncompressed teacher network, and you use the logits or intermediate features as a teacher for a compressed network. Then there's pruning. We also heard about that. You remove single weights, channels, or even layers from a network. Then there's neural architecture search. We also heard it today, where you would like to define the search space, and then within the search space, find the best configuration. And then there's quantization, which is actually my favorite method, but I won't talk about it today a lot. And here we can reduce the precision of the weights and activations to reduce memory requirements, but you could also reduce the precision in the computation itself to lower the power consumption. And last but not least, there's weight sharing, and you can do weight sharing within a layer, for example, by cluster compression, but you can also do it across layers. Just to give you an impression, if I talk about compression in the following slides, you know what I mean. And this list is not complete, but I guess these are the most common techniques. So now, if you want to solve a task, what are you doing? You want to optimize the accuracy, so the higher the accuracy, the better. So plot on the right-hand side. And you want to increase the frames per second of your deployed hardware as much as possible. And here on the right-hand side, I show a so-called Pareto optimal front. This means these are the best trade-offs. And usually you look into literature and look for this Pareto front, where to find it, and then you select a neural network configuration that lies onto the Pareto front. But this Pareto front is actually generated by evaluating networks on GPUs. What you can now do, you can compress these networks. And depending on the configuration of the compression, you can either be better than the Pareto front, so a better trade-off, or you can be worse. But of course, we don't want to do something that is worse. So in the end, for your target application and your target hardware, you also want to choose the Pareto front. Note that here, this is a Pareto front on the target hardware compared to the blue one, which is a Pareto front in the literature, usually on GPUs. Now you may think, okay, that's the best we can do, but this is actually not true. So consider a data point that is maybe not on the Pareto front for the GPU, but maybe this architecture is very good to compress, and you can arrive at a better trade-off on your target device. And this hopefully motivates you why this end-to-end hardware algorithm co-design can be beneficial. And now I said, there's a lot of craftsmanship involved. So here it's a gray error, but doing this gray error right and having it long enough on this graph is really hard. And usually what you have to do is you have to include all the compression, all the hardware constraints into network training, and this is called quantization-aware training. So for quantization-aware training, you usually get the best results, like I said, but it's also a very computational expensive because having a model of the hardware costs a lot of runtime. And also the requirements are quite strict. So this means you need to have access to the full data set. You need to have access to the original training graph. And usually you also have to use the same deep learning framework as the original network. But if you interface with customers, then the world looks very different. So then you have a hard time to make this gray error long, because then you're usually limited to post-training quantization. And this means your data is limited, usually to a couple of thousands of examples, due to IP reasons, due to the sheer scale of data sets that you can't transfer them anymore. And sometimes the customer maybe trained its network with MATLAB, so then you run into trouble if you only know PyTorch. So this is why the community came up with the unified description of network graphs, the Onyx graph. And what is usually done is that the weights are fixed, or rounded up or down, and the calibration parameters, so these are the scales for quantization, these are optimized. But we can do better than that under the same constraints. We can, for example, use knowledge distillation as explained before. And by that, we have to spend a little bit more training time, computation on that, but usually we get a better task accuracy. And I see this as a good trade-off between the quantization-aware training, which is usually required to get the best results, and the PTQ paradigm that is also lived, for example, by the MLPerf competition. And now I would like to jump a little bit deeper into this PTQ-KD method. So it's not limited to quantization. Because of the name, quantization-aware training and post-training quantization, you could generalize this term to compression-aware training or post-training compression, right? And what we observe is that if you have multiple stages of compression, usually it's beneficial if the initial drop after compression is small. And then you recover from that small drop and then you apply the next stage of compression. And this means if you have a training pipeline and somewhere you have a huge drop after compression, after initial compression, then it would be wise to split up that training pipeline. And I can give you an example for that. Here, there's a neural network. In the bottom, there's the input. At the top, there's the head of the neural network. This could, for example, be an uncompressed floating point 32 network. And then you could say, okay, I quantize the network a little bit, maybe to 8 bits. And then after that, in an additional stage, I quantize it further, for example, to 2 bits. And by doing that, usually you get better results in the end. But you could also do this differently. Instead of applying the KD loss at the head of the network, like shown here, end to end, the full network, you could also say, okay, as an initial stage, to reduce the drop, I first compress and fine-tune the first compartment of the network, and then the second one until you reach the full network. And this is also something that we didn't came up with, so this also exists in literature, both cases, but I would like to skip this slide because we are running out of time. So this works And I rather want to show you our results on this. So on the right-hand side, you can see the accuracy over the runtime. And what we did here, we compressed the network in blue by compressing it at once and fine-tuning it. And in red, if you compress layer by layer and fine-tune afterwards. So if you look at the red line, you see that it drops after compression, and then you fine-tune it and can recover it. And the final result is better in terms of accuracy than compressing and fine-tuning it at once, and takes less time. But now, of course, you can even do better than that. Avoid these drops in accuracy when compressing. And this is what I would like to talk about now. So with colleagues at Bosch, I came up with a pruning technique. So we published that at the ICLR conference in 2022. And this technique is called SOSP, second order structured pruning. And the idea here is avoiding that big step, and avoiding to have multiple stages means we do it in one shot. So it's a one-shot pruning method. But if you want to do it in one shot, you would like to know, if you prune one part, what is the effect on all the other parts of the network? And to capture that information, we use the second order correlations between the structures that we want to prune. And this also allows us to do global pruning. So this means there's only a pruning rate defined on network level, but not like it's usually done on layer level. So the technique itself then decides how much to prune in each layer. And we do that structured, so this means on a channel basis, but you could also apply the same method for unstructured pruning, 2 out of 4, 4 out of 8, layer pruning, or whatever. And if we have time at the end, I could also have a short discussion about how this method could be actually used for neural architecture search. And to actually get these correlations, what is usually done in literature, so there's the seminal paper, Optimal Brain Damage. They also used second order information, so the Hessian, but they used only the diagonal terms, so they're missing all the correlations. And if you look in literature, there are some trade-offs, because computing the Hessian is super expensive. They then use block structures of the Hessian to capture few correlations. But what we did in our study, we are capturing the full Hessian and all correlations, but we applied some approximation method to compute it. So what is the objective? We have a network with a loss function L, and the parameters of the network are theta. And now we have a set of prune structures M. And actually, we want to minimize the absolute difference of the unpruned and pruned network. And to do that, we would like to compute the saliency of the structures, and this is usually done by a second order Taylor expansion. And what we then did, because computing the Hessian is quite expensive, and going to high pruning rates, we could then approximate the computation of the Hessian with the so-called Hessian vector product. So this is the core ingredient of our study. And by doing that, we can reduce the complexity from the second order method to one that is similar to a first order method. And now we can look at the results. So here on the very right-hand side, we see the accuracy on ImageNet using a ResNet50 over the pruned parameters. And yeah, we surpass all other literature at that time. And on the left-hand side, you see how we did it. So we initialized the network, trained it, then generated the pruning masks from the trained network, applied it again, and fine-tuned it. And now I would like to dive a little bit deeper into that. So at the beginning of presenting this method, I said, okay, now we don't have a constant pruning rate across all layers. And this is actually something we see over here in the histograms. So this means if we look at the rightmost one, we see that the pruning rates differ a lot across the layers. And then what we could do, we could identify those layers where we have a low pruning rate, because these are the layers that are not that much over-parameterized compared to the others. We can select these, we can say, okay, we just double the width, so double the number of channels for these layers, and train these networks and prune them again. And this is exactly what we see here. So we have a neural network, we train it, we generate the masks, we identify those layers with low pruning rates, we widen these layers, then we train it again, generate the mask, apply the mask, and fine-tune it. And of course, we want to have a fair comparison, so we also made the original network wider, such that the overall numbers of parameters is sustained. And if we now look at the accuracy, we see that by applying that procedure, actually, we find a better pruned network. All right, so in a nutshell, it's good to end-to-end optimize the deployment chain that we just saw. I think there's a lot of potential there. We already saw some examples today, but I think we could even see it in a more holistic way and also include the configuration of the hardware. There's a wide spectrum of QAT and PTQ methods with pros and cons. Be aware to choose the right one for what you want to do. And in the end, there are sophisticated pruning models that could be used for neural architecture search. Thank you for listening.
Thank you very much, Thomas. Yeah, I think we have time for 1 or 2 questions, and then it's lunch. So, please.
Yeah, you have presented a global pruning technique and a local quantization technique. Can you elaborate a little bit why you use these local techniques that execute step by step for quantization and global technique for pruning? Or would it be better to combine it? You showed that the pruning, you have one-shot pruning approach applied. It could also be co-applied quantization. Would it be possible?
Yeah, so this could be a next study. So you could also use the same saliency instead of pruning. You could use it for quantization, right? Say those structures that are not important for the output of the network, just quantize them aggressively. Yeah, definitely this is something to do, but yeah, you have to do it, right? It's a nice idea.
Time, of course.
Good idea, yes. Mm-hmm.
All right. I think there's a question there. Sorry.
Okay, found the quantization about training quite interesting, where you go layer by layer and reduce the precision instead of doing this for the whole network. How do you exactly do that? So you start with the input layer and reduce until you reach a point where the accuracy drops, and then go further, or what is the schedule here?
So here it's not mixed precision. So it's one precision.
Something like that. That would be my second question.
Yeah. So it's not mixed precision here. So you could extend that to a mixed precision scenario, but here it's a single precision or a single.
Reduce it in several steps and then go to the next layer.
So you compress that layer with your fixed recipe, and then you fine tune it, and then you go to the next one, and you do it step by step. And this gives better results than compressing the full network and then fine tuning afterwards.
Right. So last. Okay, we can do it offline. All right. So, Thomas, thank you very much for presenting here, and of course, also getting up to another workshop. So, thank you very much.